So my name is David Greene. I work in the compiler group at Cray Incorporated, soon to be in St. Paul, Minnesota. We're in the suburbs right now. And I'm here to talk to you basically about our experience with LLVM in the high performance computing world. So I'm going to start off just describing what that world looks like a little bit, some of the challenges that we face that are somewhat unique, how the compiler works in all of this, and then talk about our experiences with LLVM and some praise and suggestions and things to think about. And feel free to ask questions along the way if you would like. So what is HPC, high performance computing? It means fast, balanced, and scalable machines. So hundreds of thousands of processing cores, petabytes of memory, petaflops of processing power. Basically, we build machines that no Cray employee could ever afford. But you can buy one on eBay. And we want to push the envelope of science, handling barely solvable problems that nobody else has been able to tackle. And we have some great customers that are really willing to wrestle with us to make this happen. We work very close conjunction with customers to both design machines and software and all that kind of thing, and there's very good communication. And these have to be easy to use, relatively. Because scientists should be doing science, they shouldn't be doing computer science. And this is really a key. It's becoming even more and more important as these machines are getting so complex that there has to be an abstraction layer, there has to be tools that help the scientist get their work done. And because of that, software is king. These machines do not run without an excellent software stack from the OS on up, all the way through libraries, compilers, all that kind of stuff. So software is really what makes these machines run. This is a machine that was installed at Oak Ridge National Lab it started in 2005, I believe. It was the first machine to hit a petaflop for open science, for doing interesting things. And it's of a scale where they had to build a building to hold the computer, right? So that's a rendering of what it looks like. And here's how it's progressed in the years. So we started off with a 26 teraflop machine. We're now up to 1.6 petaflops. And what Oak Ridge wants to see things go is an exaflop by 2018. That's not very far away. So if you calculate this all out, it means 38,000 times performance increase over 13 years. And if you do what members of our media friends like to do and use Moore's law in the incorrect way, to say that processing power doubles every 18 months, you would predict a 512 times speed up in that period. So clearly, we are, our customers want to break way beyond Moore's law. So that means a lot of stuff to do. Real quick, these are some of the things our customers do, and I wanted to highlight climate modeling because that's in the news quite a bit. There's a lot of controversy, but the thing I want to highlight is there's been a lot of news reports about changing results or scientists finding new things about these climate models. And that is because Cray and other companies are building machines like this. The climatologists can literally model things they could never model before. And we've been told this over and over again. So yes, it does actually have a real world impact. So our group, we really have 4 challenges. We've got to keep our users productive. That means we have to provide excellent support for languages and the tools that they use. In particular, these customers can sometimes have enormous codes. So there's a story that another member of our group likes to tell about when a customer code hit a particular limit in the compiler because it had more than 10,000 vectorizable loops in one function. So this is the scale of stuff that we see from customers. And feedback to the customer is really important. So performance analysis tools, how do you take something running on 500,000 cores and produce some information that is understandable by a human being about, here's where your code was slow. It's a very, very hard challenge. We obviously want to use the machine's power efficiently. People don't buy $100 million machines and then want to have them sit on the computing floor. So memory bandwidth is usually the bottleneck for most of these codes. Vectorization and parallelization can help either mitigate that or in some cases eliminate that. And we found that in our experiences with LLVM, that instruction selection has been pretty important. Our group is basically at the center of securing wins, securing customers. And it's not unusual to have somebody come into my office and say, we're working on a bid, it's due on Thursday, and we need this much more performance. We think you can do it this way, go. And then we go off and try to figure out how to do it within a couple of days. And then, of course, we got to keep ourselves sane. So that means we have tons and tons of debugging hooks and IR dumps and everything in the compiler. LLVM is really at the center of this work now because most of our products are x86 based. And we're a small compiler group. And we went through internally a very extensive and very hypercritical review in the company as to whether we were going to do a custom x86 compiler. We'd done compilers for our own vector chips and for other machines in the years past, but a very rigorous review. And there were people very high up in the corporation that said, you guys can't do this. And LLVM made it possible. Within 6 months of actually downloading the LLVM tarball and sort of integrating it into our platform, we at least had a functional prototype. It had lots of bugs, it didn't run everything, but it worked. And that impressed a lot of people. And that's, then people said, okay, go. So what does LLVM let us do? It lets us keep a lot of work we've done over 30 years. Front ends, optimizer. We can fully support the Cray machines. In particular, we have custom network hardware that the compiler needs to understand, and third-party vendors can't give that to us. So having our own compiler is really important there. And we can rapidly respond to customers, as I noted earlier. The optimizer component of the compiler is called PDGCS, for Program Dependence Graph Compiling System. It sits right in front of LLVM, basically, and does most of the optimization. And LLVM we use mainly as a code generator with some of the optimization passes turned on, but not that many. So that's our structure right now. Oh, this was not supposed to be animated, but okay. So as far as some people have been talking about vectorization, and here's how we've approached that problem with LLVM. So we have our custom optimizer, which knows how to do data dependence, knows about control dependence, and profitability with some target information as to whether it's useful to vectorize a loop. And then we have an interface layer which does the translation from the optimizer's IR to LLVM IR. We do some degree of machine legalization there, what typically legalized types would do, and I'll get into why a little bit later. And then we have intrinsics. We've invented intrinsics for unsupported operations, particularly some of the SSE4 masked operations where you can't currently represent a masked operation in the LLVM IR. We have to resort to intrinsics to do that. But for the most part, it's a one-to-one translation. LLVM, as I said, mostly codegen, some legalization, obviously, to make it work with the target, and a few transformations along the way. So last year, for those who were here last year, there was a really cool demo from Adobe of The Legend of Zelda running on a Nintendo emulator, running under Flash, and being jitted by LLVM. And I thought, wow, that's really cool. I gotta come up with a similarly cool demo. So here it is. We vectorized and generated code. Whew. Yeah. But yeah, this actually does work. It's been in the field for almost a year now. Customers are using it. They're using it on real machines. They're getting real work done. And this is, our compiler is C, C++, and Fortran. So it's, in a previous talk, someone said they weren't interested in Fortran. Well, we have customers that are very interested in Fortran. And we had to make it work with LLVM. So here's an interesting case study that a guy sitting two doors down from me worked on. So there's this code called GTC, which is used to model the ITER fusion reactor that's being designed. And they wrote a paper about how they got a 2 times speed up on that code over the previous best on the Cray machine. And the previous best was with a non-Cray compiler. And so the paper that I linked to mostly talks about I/O and things like that, but there were compiler improvements that were very important. In particular, we vectorized more than other vendors, and particularly on small loops. We were able to vectorize small trip count loops efficiently enough that they pay off on the x86. Memory bandwidth improvements were really important, so things like prefetching, which Dan mentioned in his SCEV talk, and reuse analysis, so trying to determine what data is in the cache, what's not in the cache, what data should we mark to just bypass the cache because it will never ever fit. And then kind of tied into that, instruction selection. So at the time, the chip was an Opteron 10H, which has some really nice alignment properties on SoC instructions that the Intel chips are far more restrictive. So we had to go in and hack TableGen and introduce new patterns to actually say, yes, it's okay to have an unaligned SoC memory operand on an add, things of that nature. And non-temporal moves to say, when we store this thing, don't even bother going to cache, just go to memory because you're just gonna dump something else out that's more important. And those two things were really, really huge in getting good performance on these Opteron chips. So what has been our experience with LLVM? It's been good. It's been very good. This was really Cray's first foray into a collaborative open source community. We've taken open source things before, but this is really the first time the company has said, okay, we're going to interact with this community and we're going to send patches back and we're going to bring new stuff down and radical concepts like that. And to your guys' credit, it's been really a nice community to work with, very helpful. The architecture of the compiler is great. It's easy to plug things in. Very few bugs that we ourselves didn't introduce, mostly by creating some invalid IR. And scalar evolution, I just love it. It let me do important things for Opteron, and Dan gave a really good talk on that just before lunch. Bug point, I've also really loved working with. It's nice to be able to reduce a 2,000 line function down to something manageable. TableGen has been pretty cool, and the documentation has been much better than other compilers I've seen, but still not good enough, as I think most of us would agree. So what are the problems we've run into? We'd really like to see some kind of roadmap as to what major features or what major changes are anticipated to come in the next release or the release after that. And we're not expecting commitments or anything like that, but just a general idea of what are people going to be working on in the next release, so we can do some planning when we pull down the next version. The scalability is good, but when you have things like 10,000 vectorizable loops in a function, I'm still working on a bug where legalize literally runs for 2 hours doing its job. And that's why in the previous slide I said we do some legalization beforehand, because the stuff is just so huge that sometimes LLVM can't cope with it. Not going to help. Not going to help. There are untested code paths, unmaintained code paths. We were interested in some of the other schedulers, for example, and they just totally blew up. So that's an issue. TableGen, I think, is really great. I've even contributed some stuff to it, but I think there's a lot of features that could be added to make it much easier to work with. I'm willing to work with y'all to do that. The documentation, it's easily gets out of date as things change, APIs, that sort of stuff. And in some cases, it's non-existent. It's still there really is no document about how to write a code generator. There's some table gen documentation, but it's very, very limited. The API fluctuation has been an issue for us, and I've brought it up on the email list before. We've debated it, but it really is painful when we pull down a new version and integrate it into our stuff, and we get bugs, and we have to figure out, is the bug there because it was in the upstream, or is the bug there because the API changed and we're using it wrong, or is the bug there for some other reason? It would just be nice to cleanly separate those things. So if we had some kind of policy of deprecation saying, this API is going away, we'll keep it for the next release, but then after that it's gone, it would at least allow us to separate out those problems, which would make integration much easier. Right now, it takes us at least a couple of months to integrate a new version of LLVM. It's not a trivial process. We would like, and we are working on more specializations for microarchitecture. Right now, the x86 backend is pretty much Intel specific. There's very little in there that takes advantage of features of Barcelona or other variants of x86. And in particular, when it comes to the memory system and how the caches look and all that sort of stuff. And more debugging hooks are good. It's great to type LLVM-debug and then parse through a 30 gigabyte file. I've had lots of fun with that. And the selection DAGs are a little bit hard to grok for me anyway. They're great, they're useful, all that, but just some nice additional debugging stuff would be helpful. And visualization, I always love visualization. Let's see. So what are we planning to contribute as Cray? We say we want to be collaborative. It is my job at Cray to do the AVX implementation for the upcoming Sandy Bridge and Interlagos architectures from Intel and AMD. I'm working on that. I got pulled away for a couple of months doing something called the LLVM 2.5 integration. I'm back now working on AVX full-time, and Larrabee instructions look a lot like AVX instructions from what I can tell, so I'll probably throw some of those in as I go. Part of this work is actually rewriting or refactoring the existing SSE implementation because there's a lot of inconsistencies between how an add looks for SSE1 and how an add looks for SSE2, and it was easier to just kind of integrate everything and have a simpler specification. So that's been my goal. So I'm piecemeal sending things up on that as we go. I have a huge queue of debugging type improvements. So a circular buffer to hold the debug output, so you don't need to look through 38 gigs and can just look at the last however many lines you're interested in right before you crashed. I've got a few hooks that let you say I want an IR dump before or after some pass runs. You can specify that on the command line. Similar hooks to say for this pass I want to run it n times, and then you can sort of do your binary search to find out what was the coalesce that caused the bug. A lot of improvements in ASM annotations, so I added something a few weeks ago for putting line numbers into the ASM, and there's even more stuff coming of that nature to help the user and help us map back the code that we generated back to the source. And I've also done some work with BudPoint to work with reference compilers that aren't GCC, and the main reason here was Fortran, because Fortran has no application binary interface defined anywhere. So you quite literally cannot interoperate with any other compiler. So it's impossible to take compiler generated by the Cray Fortran compiler and compare it and link it to code generated by GFortran. It just won't work. So I needed to add something to BudPoint that says, here's a different compiler to use as you're doing your good bad analysis. A different compiler or a different linker or whatever it takes. So I'll be sending those upstream. Hopefully they'll be helpful for people. As I said, we have some Opteron enhancements that I will be sending, some memory system models about the cache and so forth, and of course lots of bug fixes. The trick here, whenever I send a bug fix, I invariably get an email back from Chris Latner. Do you have a test case? Well, yes, I do, but it's not useful for you because it references some Fortran library with an interface that you don't have. And so how is that going to work? Sometimes I can translate it to C, and sometimes I can't. And it just uses intrinsic Fortran stuff that doesn't interoperate. So there's an issue there. I don't know what the solution is, but something we need to think about. So looking forward, as we all know, the architecture landscape is changing pretty radically with GPUs, with Larrabee, which is, I would say, quite different from a GPU as we think of it. Accelerators, many core, we're all going to be facing this problem of parallel algorithms. And how does the user write it? How does the compiler discover it? All of those kind of questions are things we're going to be dealing with. And so from my vantage point, some of the things that LLVM really needs is some idea of predication in the IR. When you're looking at vectorizing codes, you're not going to get very far if you can't handle conditional code. And the way to handle conditional code is to predicate. And right now, the LLVM IR doesn't support that directly, so you have to resort to intrinsics, and that has all sorts of issues with ints combined doesn't understand them, and yada yada pass doesn't understand them. So it's just kind of ugly. It works, but it could be better. And I'd like to see a few more powerful vector operations in the IR. We've made some progress with shuffles and that kind of thing. Gather scatter would be really nice to have, and something that lets you mix scalar and vector. So I want to add a scalar to a vector, or I want to shift a vector by a scalar. Those sorts of things is stuff that comes up when you want to vectorize codes. Lots of people are talking about doing parallelism in LLVM. How does it extract it? How does it discover it? We've done this. I've actually worked on 2 different compilers while I've been at Cray. One, the PDGCS compiler, which I mentioned, uses a very high-level IR called a program dependence graph. And it explicitly shows you loops and if statements and blocks and that sort of stuff. It's very nice to work with. Trying to do a loop interchange or a loop collapse or fusion or fission on a control flow graph. We had a compiler that did that too, and it's pretty ugly. It's possible, lots of people have done it, but it's something to consider as a higher level IR for that kind of thing. Error messages are really important. Users want to know what you did to their code, and particularly if you couldn't parallelize, why. They don't want to know I couldn't parallelize. They don't care. They want to know why. What caused you not to do it? You have to calculate dependence information for loops in order to determine whether you can parallelize. Some compilers try to maintain that information through all of the transformation phases. We do not. We maintain it as long as we conveniently can, and then we just drop it and recompute if we have to, because we found it just to be too complicated to try to maintain, and then the bugs that it introduces are so subtle that it was just not worth the time trying to debug. And a visualization of the IR is always good. This is an example from the Cray optimizer. This is the control dependence graph. And let's see if this laser works. No, not really. Okay. So these circle nodes represent loops. The sort of house-shaped nodes represent if statements. And then you see the arcs between them. And when you're working with a code of 1 million lines, it's just much easier to understand a hierarchical form like this than a control flow graph, which can have arbitrary edges and all of that. So finally, when we started out this LLVM project at Cray, there got a lot of questions. What's LLVM? What? Huh? What? Why are we doing this? So I finally did an ad campaign, which I posted some ads on my office door, and here's one of them. So you can go enjoy yourself by the beach, and not have to worry about your code. Another forward-looking, we're ahead of the game, and finally, here's the bottom line, and go fast, and that's what LLVM means for Cray. So we're hiring. If anybody is interested, there's a website here. You can contact me. Like I said, we're a small group. We're a growing group. And the advantage there is you'll never work on a boring project. I'll just put it that way. So that's it for the presentation. Does anyone have questions?
Thanks very much, David.
Thanks.
And again, I'd like to remind everyone, it was a perfect segue to the BOF in the piano bar to talk about vector code generation. If you want to follow up, feel free to head over there.